Hello, welcome to the stream. It is another Sunday, beautiful sunny day today here, and we are going to do some more essentials of compilation. So let's get going. Today we're working on functions. So we started chapter 7 a few weeks ago, and that was adding functions to the language. So function definitions and calling functions. And today we have a very important but potentially challenging task, which is the language that we're building is building a compiler for is a variant of Racket. Racket is a Lisp, and but it compiles, the language compiles to x86 assembly, and Unix ABI calling conventions for C and so forth specify a certain number of registers for passing arguments to functions, and there are only 6 of them. So if we have a function that has more than 6 arguments, right? We're going to have a problem. Now, the typical way that you handle this is you put those additional arguments on the stack. However, we want our language to have efficient tail calls, which means that essentially if the function calls itself in tail position, we basically repopulate the registers for the next iteration, and then we jump back to the beginning of the function. So if we keep putting things on the stack for the the contents of the arguments, then we don't have efficient tail calls because we're creating a new stack frame every time, and we don't want to do that. So the solution that the authors give, and I'll jump to it in a second, is that you turn that 6th argument into a tuple, and so you basically heap allocate space for the rest of the arguments, and then you make that 6th argument be a tuple, and that tuple is basically passed by reference. So we're going to have a look at that. Let me switch over to the coding screen here. We're following along in the book if you want to keep up. We're in chapter 7, section 5, limit functions. So, by calling conventions, we're limiting the function parameters to 6, so we don't need to use the stack. And that means that we're going to put vectors into the 6th position when there are more than 6 arguments. So, let's have a look at that. And so what's interesting about this, and you'll see it in the prose here about this. So if we have any number of arguments, then that 6th argument gets turned into a tuple of the 6th of a vector. So a vector containing the 6th argument all the way to the nth argument. And that's how we transform the function definition. But then when we get to where the functions are called, we also need to transform the invocation. So if we have a function application that has let's say there's 8 arguments. It has all our 8 arguments there. We take 6 through 8 and put them in a tuple, and that becomes the 6th. Okay, so that's where it's called. But then also, because we've turned this function definition, we've changed its signature, basically, we need to go through the body of that function and turn all of the references to those original variables, those argument names, into indexes into the vector that we just added. Okay, so let's read this real quick. Yeah, so each function definition with 7 or more parameters is transformed as follows. where the body is transformed into body prime by replacing the occurrences of each parameter xi, where I is greater than 5, with the kth element of the tuple, k equals I to the negative 6. I minus 6, not negative 6, excuse me. So, so that's like, we'll need to build, on the function definition side, we'll need to build a list of the arguments that are beyond, so the names of those variables that are beyond the 6th. And then we will need to replace all of those with, vector ref, basically. So here, var, this is the transformation they're saying. Var x of I goes to vector ref, and then, yeah, this syntax bit is kind of a pain. Yeah, so then we have to go and transform the function calls. Okay, so this doesn't sound like a lot, but we're going to have to go deep into the into this transformation. And after that, hopefully we'll have enough time. We'll get to remove complex operands, which, remember, turns it into the monadic form. So primitive operations only have atomic arguments, and everything else is turned into lets. And function calls are considered complex operands. So we will need to handle those. All right, let us go to the editor. And so last time we did this reveal functions pass, and we did some tests for it, which is good. So this was just transforming all of those applications, those function applications, into from a variable name into a fun ref, right? So let us go. We're going to do this pass. So let's go ahead and create the limit functions pass. Limit functions. Okay. And we're going to import EOC langs lfun. Do we have we had an update. lfun ref as L. Okay. And what we're going to do, let's make a function that is called limit functions. And this is going to do, our P is l.program, right? And we're going to produce an l.program. So this is a in-place transformation. We're not changing the semantics of the language. So we don't need to produce a new language. Okay, so what do we need to do? We need to, I think, first of all, transform. We'll do this in two phases, right? We'll transform all of the function definitions. So remember, our l.program is just a list of definitions. Okay. So note that the arity here is interesting. We'll probably have to update those fun refs as well to where anything is greater than 6. We change it just to 6, such that, you know, it's got that tuple there. Yeah. Okay, so let's go through and let's find all of the functions. Let's maybe do a bit that is like transform we'll just call it limit function. Let's do let defs is list map. So this will update all the function definitions. p.defs. Limit function singular. Okay, so then we have an updated set of definitions for the functions that have updated arities. We probably need to yeah, I think we can. Let's do that, and then maybe we can do the function application bit in the same pass. Yeah, so let's just do p.defs, and we'll pipe it to list map limit function. And then we'll pipe it. Come on, pipe, please. Oh, that program. Okay, so let's import Gleam list, and then let's generate this function. Okay, so this takes a function definition. So I think that if we get, so we'll have two bits here. Transform the definition if it has more than 6 arguments. So that's a pretty particular one. And then we'll transform all function applications in the body. And since we know that we are going to transform all the functions in one go, we don't need to know whether that a function, because we've already done this reveal functions pass, which turns the variable references into function references. We don't need to do anything with keeping track of what functions exist. We've already validated that all of those exist. We would have gotten an unknown local variable if those transformations hadn't succeeded. So here we go. We can just, we've established some baseline invariance already, so we can just go ahead and do this transformation with confidence. I think that's what I'm trying to say. Okay, so this is going to be 2 passes. So let's look at case definition arguments. And what we're going to do is we're going to just pattern match A, B, C, D, E. So that's 5. F, rest, right? So this is going to say these are the 6 arguments, and there's actually, we probably need to do E rest, right? Because then this says this is more than 6 arguments. This could be an empty list. Also, we could do list split. let's look at the standard lib. List split at index. Okay, so 0 is before the first element. Okay, so it's basically how many you want to take. Okay, so if we do, let's do, so in addition to transforming the definition and yeah, let's do list split six. So we get the base args, and if we get the empty list, this is going to be like, what do we want to return? We want to return from this the updated arguments and like the indices of the extra, right? So this will be, let's just return the arguments as is, and then we're going to do we'll just say this is an empty dictionary, because what I want to do is so there's our 6 arguments, and then if it's anything but the empty list, we need it to do here so that I can think about this. So basically what we want is let's look at this. So the vector ref is a k minus 6. So vector ref, I think, is 0 indexed. Yeah. I don't know if I feel comfortable calling this toop. I want to like create a unique name there. Maybe I guess we can call it tube. I'm not really comfortable with that, but we can guarantee that all the argument names, because we did the uniqueify pass, right? All the argument names are already unique, so this will not collide with anything. Okay, so let's look at what the arguments would look like. So what we will have is A, B, C, D, E, and then toop. And we need to define what toop is. What toop is to do. Okay, and then we're going to have a dictionary of So the arguments is a, let's see, list of string to type. So what we want to do is go this is just going to be tup, and then we're going to list map from over f extra, so we're concatenating that, and we're going to take pair.second. Does that give us the right type? Okay, we'll just say dict new here, just to make that happy. Get rid of the to do and see what happens. Okay, so oh right, so what we need to do is say l.vector_t. Okay, we need to import UC langs lfun vector t. Okay, so this is in order to be a type, it has to have a variant that's correct. Okay, what's wrong there? Okay, we're going to import Gleam dictionary. Okay, so there's actually a problem here. I need to do this because that doesn't actually split it into, it returns a tuple. This is part of the problem. Now it should be able to type that a lot better. Okay, and then I'm just going to say this, and this is, we know that it's either going to give an empty list here and some arguments because it's fewer than 6, or it's going to give 6 plus whatever else is left. I'm going to say panic as list.split with more than 6. We'll just say list.split in limit function. That should never happen. I want to make sure that this is the case. So if we do list split 6 and we give them 6, what we're going to get is an empty list on the second. And then this will never be more than 6. And then this will be, you know, whatever is left. Okay, so ltup is exactly what we expect. So now we need to do so we're going to say the indices is going to be, we have index map. Yeah, so we'll do index map over f.extra. And this is going to be, this is a single argument. What we want to return, I'm sorry, so index map, the index is the second argument. Okay, so what we want to return is arg.0 and index. And then we want to do dictionary from list on that. Let's just put that in the next line. Okay. So now I believe we have what we need. So let's pretend that we've done the other bit. And let's say L definition. And we're going to say arguments gets updated. And we'll say body gets updated. And we'll just do to do here. So that should handle all of that. Okay. So now once we have this, we need to basically recursively process the body. So let's say limit function body, and we're going to pass definition.body, and we need to pass the arguments, right? No, actually we just need to pass the indices. Okay? Because we don't really need this. We can assume that the additional arguments are named tup. I don't really like that, but I almost want to do something like JavaScript where it's like actually called arguments. But let's generate that function. So I'm going to rename this to expr, so that we can do case expr and then fill all the patterns. So the only things that we need to be concerned about are any nested expressions, and function refs. So apply, we'll need to adjust, and we'll probably do a case split there. We need to, so let's move these up to the top. Oop, that's not what I wanted to do. Okay, so var and function ref need to be changed. Apply needs to be changed. The others just need to be like recursively transformed. Okay, so var, so we're gonna do case dict get indices name of OK I. Then what we need to change this into is this. So we need to do L prim vector ref, and that is takes tuple L.var tup and L.int, because that's still an expression I. Okay, so let's read this bit again. Okay, so replacing current recurrences of each parameter x sub I, where I is greater than 5, with the kth element of the tuple, where k is I minus 6. So yeah, so it'd be 0 if it's 6, and like our index map should bear that out. Let's look at index map real quick and make sure that that's correct. Right, so the first element is 0, second is 1, and so forth. That works out perfectly. Okay, and then if it's an error, right, then we just return L.var name, or we can return the unchanged expression. So funref. This is just going to change to funref name arity max arity 6, right? So the fun refs, we're clamping them down to 6. Easy enough. Okay, now apply. We don't really need to change the function because we haven't made that atomic. This is a full expression. But what we do need to do is change this into a, like, the vector bit. I think that this is going to be simple. So we will do lapply function, and then okay, so let's do case list split arguments, and we're going to split it at 5. No. Split it at 6, like we did above. And we'll just rename that. Okay, so if we get empty list, then we'll just return the arguments unchanged. If we get I'm going to make this case. Okay, we're going to get A, B, C, D, E, F, rest. What we're going to do is we're going to change this into A, B, C, D, E, and then L dot vector of F dot rest. And this will be panic as list split in limit function body. Okay, so this actually needs to be L dot prim, right? Because that's a primitive operation. Okay. So yeah, so we basically moved the 6th into a vector with the rest of those things, and all 5 of the rest of those are kept directly. Okay, so now we just need to go through and all the things that are direct, we're gonna have to do a case. Let's do, we'll recurse here. Op and indices. This is a pattern that we do a lot. It is just recursively walking the tree. So we'll do something similar here. And I want to rename this function limit function expression. Okay. Hello, Chris. How are you? Good to see you. Indices. And I'm just going to copy that. If true is, take the if true bit. If false. Good. Back from Rust Week, another traveling, so catching up on rest. That's great. I'm glad to hear it. What were you doing at Rust Week? I would love to know what's going on there. What even is Rust Week? I hadn't heard about it. Result. MC'd one day, day one track, and attended the NCOF with Bevy. Rust NL? Oh, so it was in the Netherlands. That's pretty cool. I had not heard about that. Very nice. I think there might be a bit here that we need to adjust, which is when we construct this vector, we might need to put the has type around it. The problem is we have not, or does that matter? I want to think about that. It doesn't necessarily say it. Oops, it doesn't necessarily say it here in the book. It's possible that we don't. I'm trying to remember where beyond type checking that we use this has type. Let's look for it in the, yeah, ignore that. Okay. Okay, and so so we do it in right, we have it there. I want to look at the passes actually. So explicate control. Okay, tail position. Okay, so that's, we convert it. Okay, expose allocation. This is probably where it's going to come up. Because it's about injecting the allocation and the garbage collection call. It's been a while since I looked at this. Wow. Yeah, so we only care about where the has type contains a vector. If it has something else, then we just recurse. But what I'm not seeing, let's see. Yeah, untagged vector initialization is going to be a problem. So the question in my mind is, do we need to, in the type checking phase, look at all function applications and tag those? That's an interesting thought. Let's go back and look at our type check. Type check. Okay. So right, so we're wrapping the vector here. And this type check op for vector, you know, checks the nested expressions. Right, and returns, here's the expressions. So here's the thing that we need to construct, and here's the types. And then we slurp it out. But here we're constructing this after the type check phase. So I wonder if we need to call back into the type checker at that phase, or if we need to look at in the type checking phase maybe there's an easier way around this. We definitely need to put the type around this. But the interesting thing is, if we have all the definitions, yeah, I thought we could do this in one pass. Maybe what we do is well, but we can't at this level, because this function is an expression. It's not necessarily directly a function ref. Wow, this is yeah. Alex, if you're on the stream, I see your comment in Discord. Thank you. I need to think about how to deal with this, because we need the has type wrapper for allocation, and maybe I just need to scan ahead in the book and see what happens there. Right, okay, so it turns applying to call and entail call, select instructions. Register allocation, liveness analysis. There's nothing in here about how that interacts with expose allocation pass. Let me look at the graph at the end of the chapter, like usual. So expose allocation happens after limit functions, right? So if we go back up here, keep going. Okay. Let's see what they say in 7.6, because this is like, yeah, we're hunky-dory. We can just transform these. atomic expression is an immediate argument of an x86 instruction. Function application translates to a sequence of instructions, so apply must be classified as complex, right? Okay. But remove complex operands comes after expose allocation. So there's a bit missing here. I don't think that we have, because right now we have that panic in there. And I don't think that that's, we need to match on the type, right? Otherwise we are, okay, so I think we need to consider let's wrap this in curly braces. Let's call let vec is this, and then we're going to replace it. I think that we need to do L type check expr. Is that even public? Oh, but the problem is we have this. Shoot. We don't have type checking for this intermediate language because we omitted it. Yeah. That's why it's like, hey, I don't know what that function is. I wonder if we should look at typing this. And I think that if we wrap this in has type, or, well, L apply, we don't want to wrap in has type. We want to wrap this or this in has type, right? But I think it comes down to function. So let's look if we can do that. We can go back and say apply. Okay, so we try to type check the expression function. And this should be a function type. If we have that function type, when we get to transforming its arguments in limit functions, we can look at that type, because this type doesn't change across the different intermediate languages. It's only defined in the top level one, but we could make use of that. There's nothing wrong with wrapping, you know, something in has type here. It just gets erased later, but we need to carry it through. So I think that what I want to do is say has type f type. And then when we get to right, Right, so this goes through all of the arguments and makes sure that their types match up with the argument types of the function that was determined there. Okay, so now here I think we need when we say this is yeah, let's we're gonna have to make use of some more of those things. Okay, so except that's not part of this, it's part of I think what we want here is L.hasType, because this is still part of so if you remember the if we look at the type definition of our type system, there's a fun T. So we should probably make use of that. And that's just the list of the types. Okay, so let's put fun T in here. And this is going to be fun T arg types, right? Okay, I think this is a good enough solution. So we're going to say has type on this, and this is going to be vector T, and what we want is list split of arg types 5, and we want paired out first of that. All right, I've got a syntax error somewhere. Okay, I think that this will help us quite a bit. I'm going to make this an explicit variable, and let's just say let trailing args arg types list split arg types 5, right? Except that we want that reversed. We don't want the first part. We want the trailing arg types, like so. Okay, so there's still something wrong here, really wrong. What is wrong? Is it down? Oh, it's down here. Well, fine. We just need it to do. And then you can tell me what other bit is wrong. Oh, da, da, da. Found name expected one of. Oh, I need another paren there. Okay, so now it's just like, hey, this whole thing is wrong. And exhaustive patterns. Okay, so what I'm going to do here is, if there's an null apply, that has anything else, we're going to say panic as unannotated function call. Yeah, I don't know if we need to continue propagating this. But we do need to make sure that that the function application is annotated with a type. When we say unannotated, when we say untyped function call. Okay, so let's just put ignore in there. Okay. All right, and then let's do the rest of these, and we can do the limit function op. Yep. Okay. I think that's a pretty decent solution. It's really just about, like, we need to make sure that types that we need later in the compiler get wrapped around where they're important to do. So, okay. So the interesting thing there too is that we've annotated the vector allocation, but we've removed the annotation on the function, which is fine. Okay. Let us handle a while loop. That's going to be limit function expression, condition, indices, and body is going to be a limit function expression, body indices. And then the has type, we'll just say this is has type, value is limit function expression, value indices, and t. Okay, and now we can generate this function. Oops, generate that function. Okay, so read. Honestly, again, this is just recursing. I'm just going to do this very mechanical. Okay, then we'll do l.negate is going to be limit function expression, op indices, not op, value. And then we're going to have some very similar bits here, so let's try to make it as easy as possible. A indices, B is B indices. And let me copy all of those, because it's the same there. And this is all comp op. This is L.and. We should not have that at this point, but it's in the language. Got to handle it. L.not is going to be just A. Okay, and this is going to be L.vector list map fields. Limit function expression indices. Vector length is V a whole expression there? Yeah. About vector length. Limit function expression V indices. Again, like, this is not very fun code, but and then we'll do the same down here. Vector set value indices. Okay. I think that's pretty good. We might want to go back and see if there's any. Do we have any tests for lfun? No. Yeah, I think that this is a pretty decent implementation so far. But I want to make sure that we have some coverage on the type check. So we're going to need to come up with a test there. Fun test Gleam. Wait, what just happened? Why does it not find Gleam? Okay, that was weird. Oh, well, it helps if I name the file correctly. .gleam, not just underscore gleam. There we go. Okay. Alex is saying in Discord, I wonder if it'd be possible to do that limit function op code inside out. Like, yeah, I mean, to make it more fun, haha. I mean, have a look. Like, I could inline this, you know, up here in the prim. I just chose not to. I could even inline it and flatten it. I kind of like having this be a separate function, so that's just kind of a style thing. Okay, so what we want here is function application carries type test. Okay, so what I want to do is let's port EOC passes parse, right? I want to make a simple program. We're going to say assert okay tokes parse dot tokens, and then we'll put our program in here, and then we'll say let assert okay program parse dot parse of tokens. And then so we're going to write our program right here in a second. Then I want to say p2 is lfun.typeCheckProgram. We're going to say let assert OK p2. And I think I want to use the variant here, so we're going to say lfun.program defs expression. We're going to ignore the defs because I just want to use the we're going to type check program. And then it's like, oh, body. We'll say body. Okay. Okay, so then what I want to make sure is that when we have a function call in the body of the program, that that application has a type around it. Okay, so let's define, I don't know, foo. Oh, it needs to be like this. A is integer and B is integer, and returns an integer, and we want it to be this is dumb, A plus B. Okay, and then what we're going to do is our function call is going to be foo 141, of course, because that's what we do. Every program returns 42. Okay, so I want to look at let's just do an assert equals. I think that that's going to be the easiest. So we're going to say lfun.apply. Whoa. Apply. Okay. And the function is going to be has type. And it's going to be a var of foo, right? Is the expression. And the type is going to be function t. Or fun t. And the arguments are going to be integer t, and returns integer t. And then this application is going to be lfun.int 1 lfun.int 41. Okay, body. Okay, so I hate writing the AST like this. But this is what I want to check. So let's run that test. Okay. Reveal functions test. Okay, so I broke another test because I put the has type around it, around the function application. Maybe Birdie would help on AST tests. Perhaps, but I'm wanting to check very focused things. I'm not really concerned with drift, if that makes sense. I'm trying to check very specific properties, and regardless, I'll have to look at the AST anyway. So, yeah. All right, let's look at reveal functions, and I think that we can probably just adjust this test. Okay. So right, so what it's going to do is it's going to annotate, because this is an application, it's going to annotate the map function. So we need has type around it, because that's going to persist. And this is going to be a fun T. It's a very fun T. And its arguments are a fun T, which takes an integer T and returns an integer T. And the second argument this is going to return a vector T which contains two integers. Right? Because that's what this returns, a vector of integer. Okay, and then so that we have this type. As the second argument there. Okay, let's see if that fixes it. Yep, fixes it. Okay, so we got what we expected. I'm pretty satisfied with that. Now, now I think we need to make a test for limit functions that covers this properly. And then maybe we'll get to remove complex operands, and that would be useful for today. Okay. Limit functions. And we're going to have to import EOC langs L fun as L. Import EOC langs L fun ref as LFR. That's what we did in the other test. And we might need other things in here. Excuse me. Okay, so what we want to do is we want to design something that we've gone through all the phases before here, and we want something with like at least 7 arguments. I mean, it doesn't have to be really complicated. 2.6 test. Okay. Limit function, we'll call it limit function arguments 2.6 test. Okay, so let's do our dance again of, I think that we did this in here. Did we do this over here? Yeah, we made this program function. Yeah, and it just did all the passes before this. So we'll do something similar. Okay, let's import that. We're going to import shrink. We're going to import uniqueify. And what other passes come before this? The other thing that we can also do is wrong window. Sorry. The other thing we can also do is look at the web version and update that. Add the limit functions pass to that. Okay, so we have shrink, uniquefy, reveal functions. Limit functions comes after reveal functions. So I'm going to say reveal functions. Okay. So let's do define. We'll do define foo. And we need to have lots of arguments. And let's just say it returns an integer. And then let's do foo 1, 2, 3, 4, 5, 6, 7, 8. Let's do 8 arguments. Again, this doesn't have to be complicated. It just has to be enough to demonstrate that both, like, all the things that we care about get transformed. F G 1, 2, 3, 4, 5, 6, 7 H. Okay. If you have a procedure, yeah. If you have a procedure with 10 parameters, you probably miss some. Yeah, and actually that's a good point. Like a lot of other languages will, Clippy in Rust at the very least will warn you if you like have too many arguments, and that's a great thing. But what it's saying is not this what we're trying to deal with is a very specific issue with the limited number of registers in the calling convention for arguments. But generally speaking, if you have that many arguments, maybe you should be thinking about how you structure your program differently, right? So I think it's a really good point, Alex. Okay. I'm just going to sum all of these things. Oops. How can I do this? Let's do plus AB. And then let's do another paren, C. And this is going to be the most atrocious thing ever. D. E. And it's actually good that we put these at the outside, because what we can do, I'm gonna have to count parens, aren't I? Oh, I screwed myself. Okay, so what we can do is we can look at, like, ignore the inner part here and look at H and make sure that it, so these become part of a tuple, and then this is a vector ref tup with index 2, right? Like that's something that we can do. All right, let me make sure, just for my sanity's sake, that I got all the parens correct. Okay. We are good there. That looks really janky. What I should be able to do, though, is go to our web doodad, and then we're just going to put it in parse and just let it, yeah, so it validated that's correct. I'm going to put this text in here, and we're good to go. Yay, pretty printer. Okay, if we do the type check, we don't see the wrapper. Shrink. Okay, so we put main as its own thing. Uniquify, all those get names. Pretty nice. Reveal functions. That turns it into foo/8. And then what we're going to want to see here is we're going to add a phase, which is going to be our limit functions. But okay. Okay, so this is going to return LFR program. Good. Okay, so now we've got this, and what I want to see is let's see the foo definition. Let's say assert OK. List find. See foo. We're going to find p.defs. This takes a bool. Okay. Okay, so the name is foo. So now we have the definition, and we're going to assert list length foo.arguments equals 6, first of all. And then we're going to say assert tup vector t we're checking all the things here with the transformation, right? Okay, so it should be and this is probably going to need to be assert okay list.last of foo.arguments, right? Okay, so we're saying there is a trailing argument tup, and it has a type of a vector of 3 integers. Okay, what else? We need to look at the body, and we want to look at the prim op here. Let's do let assert here foo.body is what we want. Okay, let assert prim so that's going to be a primitive operation of plus, and then A is going to be that. We don't care what A is. Why is that not matching? Okay. And B is going to be vector ref index int2, and v is going to be l.var tup. Okay, what's wrong here? Oh, I need LFR here. Sorry, that's what's wrong. Okay, LFR.primitive operation. Okay, so I just want to make sure that, and we can expand this as we need to. What I want to see is, you know, this trailing h here is indexing into that tuple argument. Okay. So interestingly, the arguments were not updated. So we need to fix that. Found bugs. Tests are good for you. Okay. Let's, just for argument's sake, let's put, oh, did I call limit functions in my test? Helps if I call limit functions. Okay, so what we're going to do is pass that to, yeah, that was the problem. It's not that my assumptions were incorrect, it's that I didn't call the pass. Okay, so that succeeded. Let's do another bit here. And do another ignore and like do this same part. And then we'll add one more layer here. This needs lfr.prim. Love it when the language, and by the language I mean Gleam here, helps me do this ASD correctly. Okay, that feels pretty good, and that shows that we were able to map those variable names correct. So it shows a number of things. First of all, the number of arguments is 6 total. The last argument becomes the tuple of 3 integers, taking f, g, and h and putting them into that vector. And then the each of the references to those variables gets turned into this reference to the trailing arguments. Now, what we need to do is get the main. And we're going to say main. Okay, so now we need to make sure that the call to main constructs that vector. Not only that, it should reconstruct the type of, or no, it removes the type, right? So what we want to do is maybe just this. So we're going to say it's an apply expression. And this is a fun ref. I need to do not LFR, sorry. Fun ref foo and that should be 6, right? So this is one of the things that it changes. And then the list of arguments is going to be int 1, 2, 3, 4, 5, and then we'll do it. It's going to have a has type, right? And the expression is going to be l.prim l.vector of l.int 6. Oh, and I'm sorry, these need to be LFR, so let's update those. Otherwise it's incorrect. Okay, and then the type is vector t, and we had this above. We have it here. This is the type. All right, let's run that test and see what we got. Okay, so we've got a problem. Okay, so the arguments look correct. It's that the fun ref was not updated. So what we did, so I think that we need to, yeah, we just pass this through. So let's fix that and say function equals a limit function expression over the function in the indices. So that'll loop down into there, and that should fix that problem. Okay. So, oh, it's not max, it's int min. See? This is why you do tests, even when it seems like it's straightforward. Okay. So, basically that means that, you know, I don't know this is strictly necessary, but like this arity will go into the call queue that we handle later in the assembly code, and that relates to stack allocation and like and so forth. So we need to make sure that that arity is correct after we've modified it. Okay. Let's just use the Git panel here. That'll be easier. All right, let's stage all that. Okay, so what we did, yeah, there we wrap the function called types, or the function applications with types, and then we updated that test to work, and then we have, yeah. So this is chapter. Oh, but let's update the compiler, right? The compiler playground. That's the fun part anyway. Okay, so here, reveal functions. Let us add limit functions, right? And then reveal functions, limit functions. And then we're going to have to handle it here. Limit functions. String to pass, reveal functions. We need to put in limit functions. Not like that. Okay. And then interpret, we don't care. Compile. All right, so uniqueify reveal functions. Let's copy this. And we're going to do limit functions. And then after here, we're going to do limit functions. All right, so if we go let's restart Fluster dev server. Okay, so let's go to reveal functions first. Okay, so there we've got all that. Let's switch it to limit functions. Okay, so now we've got foo6, 1, 2, 3, 4, 5, and then has type vector, right? So we got the has type wrapper on things. That's good. And then over here we've got tup vector of 3 integers. And then vector ref tup1, tup2, tup0, and so forth. So we did it. Yay! Now I can make the commit. Stage all. Okay, so this is chapter 7.5, limit functions, and we did that end to end. There are obviously more tests that we could come up with, but I'm satisfied with that for now. So I think maybe we got 25 minutes approximately left. The next chapter section is remove complex operands. So what we can maybe do in the 25 minutes left is make sure expose allocation and uncover get wire all this through and that their tests pass. And then we can call it a day and we can do remove complex operands next time. Because I think that, let me go up. Remove complex operands is always complicated. We'll have to generate a new intermediate language based on Elmon Alec with fun. Here, go back, please. I hate it when that happens. I clicked something that actually jumps to a heading. Table of contents. Right, so you know, one of the interesting things about the way this book is structured is they don't it's not explicit all the time, and partly because this is a didactic book. What they're trying to teach you is not like everything you need to touch on every expansion of the semantics of the language. They just want to touch on the things that actually need to change, and there's an interesting difference here too between Gleam, our implementation in Gleam, and what you would need to do in Racket. And I think that in Racket, because a lot of it is untyped, you might not need to adjust any of the bits in those intermediate phases. But since we have a brand new language from a different module with a different type, Gleam is like, yeah, I can't just take that. You're crazy, man. So let's wrap up by making sure expose allocation and uncover get are up to date. Okay, so expose allocation. So let's change this to, okay, so this actually produces a new language. Alec funref. We might not finish that today. And I think that they hand waved over a lot of that. So here's where we were. Okay, so expose allocation. Right, so this is doing all of the vector bits. And we looked at this earlier. So I think that what we'll do is let's duplicate this, and we'll call alloc funref. And this, I think, is going to be I think what we do is we just add these. So I'm actually going to, we're going to take funref. Here, let's delete that. We're going to duplicate this, and we're going to call alloc funref. And then we're going to add, oops, we're going to add these variants. The collect, allocate, and global value. And I think that, yeah, so right, and so there's no vector construction. And we need to get rid of this. Add the missing patterns. I don't think I did an intermediate form or a pretty printing here. I think I'm just going to say doc from string and $sign name. And here I'm going to do allocate. I think we have ones farther down that pretty print. Yeah, this one pretty prints, but this is also the C-like language. So okay, so I'm just saying parenthesize that. That's fine. Here we go. So this is going to be, rather than this, we'll say it's global value. Here, let's just put to-dos here for now. Okay, global value, and then doc from the string name, and here we'll do doc from string allocate, and then amount is just an integer, isn't it? Yeah. String int to string amount, and then we'll say format type, and then we'll doc concat join. Here, I'm just going to copy this because I'm bored. Okay, and then collect is going to be something similar, from string collect, and then this, and then all this. Okay, what else is broken in here? Okay, so we can pretty print this intermediate language, and we no longer have the vector primitive operation, because what you do is you allocate and then you do vector sets. So that's what the expose allocation lowers to. Okay, but now what we need to do is where's our pass? Okay, expose allocation. So we need to say this is a log funref, and this is not ltup, but lfun. Except it's going to be lfunref. Okay, so now, rather than body, we need to map over the definitions. And probably what we'll do is we'll make this a pipeline. List map. And this definition, we're going to say la.definition. Let's just call it expose definition. And we'll make a function, expose definition. D, and it's going to take an L.definition, and it's going to return an LA.definition. And honestly, you know, there's whatever's about like naming fresh variables, but within the context of each function, that those will be unique anyway. So I'm not concerned about making sure that that remains unique across processing multiple definitions. So we're just going to say expose expr of d.body 1. Okay, and then we'll say definition. So this is going to be, maybe what we do is deconstruct this. Can you fill the labels for me? Thanks. Okay. So we can just reuse those arguments. Return body. Okay, and now we just need to deal with the things, the missing bits here. Okay, so this is about exposing allocations. This will just translate with no changes. And then this is just going to be recursion. And we will just follow the pattern we've done before. Expose expr of function and counter. Arguments C2. Arguments, and this is actually going to be list fold. Do we have a list fold up here? Like, is there begin anywhere? Yeah, let's do map fold. Say C2 arguments, map fold arguments, and then we'll do LA dot apply. Except we need to return that and C2. And this needs to return that and counter unchanged. And this will take C1. Okay. So that was a lot. But we don't have anything else to change in here. We've handled the additional constructs. Okay. Now let's go back to the test. What's still wrong in here? Oh, okay. Where was that? Let's see if I can do a rename on that. LFR. Okay. And then wherever that bug was in here. Yeah, okay. Now it should be fine. Okay. Let's just make sure that it builds. And we're going to go down to the tests. And then I think that we'll call it after this. I will probably make sure that we have expose allocation as a phase in our Explorer, because I think that's really important. And this is going to be Okay, so we need to pass this through the other phases, I think. This should be l.typecheckProgram. Let's make sure we're following the same. Yeah, we need these. I am concerned that this test is going to be hard to maintain longer term. But what we can do is wrap this, I think. I'm gonna make a this is, I think we did this before in a previous stream, but that's the body expression. So we need a definition main, no arguments, integer t is the return type, and then this is the expression in it. Too many parens. And that needs to be l.vector t, where those types are. Not re-exporting types, so what I mean is type, you know what I mean. Not Gleam types, but our language types. To your point, Willie, from earlier, that maybe like it would make sense for this to be a snapshot test. Okay, I didn't. Where's the should expose allocation test? Oh, right. I need to transform this. I think I had it commented out and it didn't. So let's change this. Let assert okay tokens is parse.tokens of input. Let assert okay program untyped. And let's wrap that. Nope. Okay. And then type check program returns a type, doesn't it? No, it just returns the program. And let's make that function call, and then it'll be 119. Okay, so it actually passed. Nice. That's good. Let's wire it up to the Explorer and then call it a day. I think this is good. So we go here. Right, so limit functions, this is going to be a new pass that we actually handle. And I kind of want to just like remove all this so that we can get all this stuff together and then have it be sorted. Okay, so we're going to make a new pass in here, which is going to be expose allocation. And that means we need to do expose allocation here. I want to see this in action, you know? I want to see it working. Okay. And then here, we'll take whatever is in limit functions, and we're going to say expose allocation. And then this will be LFRA format program. And then I think, why is that all red? What am I missing? Oh, I need, this needs to be expose allocation. Okay, so we should see, so we have expose allocation here. Let's get an interesting program, first of all. Maybe what we do is we look at that example in our test. This classic example. Okay, so main, no arguments, returns an integer. And then all of this. But you can see the allocate operations. We do collect. There's a global value, free pointer in front space end. Yeah. Cool. I think this is a great place to stop the stream. Let me put in a commit and push that, and then you all can look at it in your own time. Okay. Update expose allocation for L for new language. And then next time we'll start with uncover get, and we'll look at remove complex operands. And thank you all for coming. This has been great. Have a good one.